And welcome to Chapter 5, where we're going to be dealing with electrons in the atom. Hey, in Chapter 4, you were dealing with atomic structure, but you were looking exclusively at the nucleus, the protons and the neutrons, and the mass that they provide. You also studied J.J. Thomson's experiments and Ernest Rutherford's experiment and the historical development of those models. But in this chapter, we're going to be dealing with electrons, and it's because the electrons control the chemistry. Now, we're in 5.1, models of the atom, but just realize that we're going to be actually pulling a lot from section 5.3 as well. There will not be a set of notes for 5.3 because they're incorporated in this particular section of 5.1. You will be doing the 5.3 homework, and so you're going to need to be looking through that particular part of the chapter, but there will not be a note-taking guide for 5.3. All right? Now, before we jump into our understanding of the electrons, we need to review the concept of light, because light will actually allow us to understand what these electrons are doing. So, first of all, light travels as electromagnetic waves. They can have long waves, meaning you're going to have a relatively large distance. I'm tracing this particular wave right here. A long wave simply means that you have a relatively long distance between the same point on two successive waves. So this red wave would be considered a wave, a longer wavelength. The blue wave over here exhibits a shorter wavelength, simply meaning it has a shorter distance between two equal points on successive waves. Now, the thing about a long wave is that as it passes through space, if the waves are far apart, you're going to have fewer waves passing a given point in a given second. So longer waves have low frequencies. The frequency refers to the number of waves that will pass a given point per second. If the waves are packed tighter together, that would mean that you can pack more waves passing through a given point in a given second. So long waves mean low frequency. Short waves mean high frequency. Now, all light will behave as waves, and depending on their wavelength and their frequency, that will give them different properties. For example, if you have long waves, and we're looking at this particular diagram here, and by the way, this diagram does not show one continuous wave that is being compressed. It is simply showing the relative distances between different forms of electromagnetic radiation. So, if you're looking at this particular part down here, wavelengths of 10 to the second power meters, which is 100 meters, which is the length of a football field, some waves take a full football field to go through an entire cycle or an entire oscillation. Those are called radio waves, and obviously they're used to transmit music and information through radios. If the wavelength is more on the order of 1 meter, we would call those types of waves radar. As you get shorter yet, wavelengths down around a centimeter to a millimeter to slightly smaller yet are called microwaves, and we use those for cooking food. As you get more closely to a millionth of a meter, you'd be getting into what's called the infrared portion of the spectrum. We experience that as heat. Now, when you go smaller than a millionth of a meter, now we're getting down into nanometers, excuse me, between a millionth and a billionth of a meter. A nanometer is a billionth of a meter. Well, when you're somewhere between 380 nanometers, or billions of a meter, and 700 nanometers, your eyes are going to be picking up those wavelengths, and it's the visible light spectrum. Now, if you notice, the longer waves are the red light. The shorter waves are experienced as violet light. This is something that you're going to have to know. You don't have to know those actual numbers, but you do have to know that red waves are longer, low energy waves, where the violet are the high energy short waves. And of course, you can remember the order to these waves using the mnemonic device Roy G. Biv, where each letter indicates which color you're talking about: red, orange, yellow, green, blue, indigo, and violet. you are going to need to know the order and the relative amounts of energy that those particular wavelengths have. Of course, once again, red light is the lowest in energy, violet light is the highest in energy. Alright? Now, what you'll also need to know, again, is that light with long waves have low frequencies and low energy. Light with short waves have high frequencies and high energy. This idea of corresponding relative amounts of energy to color is really where we're going to be able to understand how these electrons behave in the nucleus, or around the nucleus, excuse me. Scrolling down. Now, the whole idea of light behaving as waves is a concept that goes back for several centuries. It was always thought, anyway, that light simply behaved as waves and matter behaved as particles. Well, Albert Einstein, in addition to his theory of relativity, also proved that light can also behave as a particle. He called these particles photons. And because light can behave as a particle, this particular model, with all its implications, gives rise to what's called the photoelectric effect. The photoelectric effect simply has light energy turning into electrical energy. And of course, many of you have solar-powered calculators or whatever type of solar-powered device. It could be a solar-powered car. Here's your screen, here's your buttons. And you know that at the top here, there's going to be a solar panel, something like that. Well, what happens is these photons of light, or particles of light, will strike the photoplate, and it will cause electrons to flow. Now, we're not going to get into the details on why this is. You can study that more in a physics class. But the basic idea, anyway, is that light can induce and cause electrons to flow. Now, here's a problem. Because light cannot behave as both a wave and a particle in terms of a model. The two models do not coexist well together. They're actually in competition to one another. The fact that light behaves as both a wave and a particle does not mean that you have a particle that oscillates through space, something like that. Alright? These are two competing models. One model is used in explaining how light can produce electrons to flow. The other model, the wave model, is used to explain a lot of different properties, including why rainbows form. Alright? But this paradox, the fact that light behaves as both a wave and a particle, and we don't know exactly how that can possibly be, is simply known as the dual nature of light. And we're going to utilize this under this idea of the dual nature of light to help unpack what we understand about the electron. And we'll do that continually in the next podcast.